In this video, Shabab, we are going to talk about a very important set of functions called singularity functions. And basically, we are going to talk about three important functions. The first one is called the unit step function. The second one is called the rectangular function rect t over capital T. This is how we write it. The unit step function, we write it as u of t. The rectangular function rect t over capital T. And the most important one is called the unit impulse function, or it has another name, Dirac delta function. Usually we call it delta function, and it's written as delta of t. We'll start in this video with the first two functions, and then we'll do a next video, separate video for the unit impulse function. Let's start with the unit step function. The unit step function is defined as u of t, it's 1 for t greater than 0 and 0 for t less than 0. So basically it looks like this. 0 here and 1 here. So this is called the unit step function. The unit step function is very important as a switching function. Sometimes we need to write a certain function that starts from 0, like a cosine wave that starts from 0. How can we do that? Either you will have to write the expression of the function in two lines. You have to write it's cosine for t greater than 0, it's 0 for t less than 0, for example. If you want to mathematically write a function that looks like this, it's a cosine wave, but it starts from 0. It's a cosine wave that starts from 0, something that happens practically, that you go in the lab, switch your generator, switch your signal at t equals 0. This is a cosine wave that starts when you switch it on. It doesn't go from minus infinity to infinity, right? It's a cosine wave that starts the moment when you switch it on the generator, right? How can we represent this mathematically? You represent this mathematically as a cosine omega t. If you write it as cosine omega t, only this means that it's a cosine wave that goes from minus infinity to infinity. But if you want to represent this cosine that starts from 0, you have to multiply by a unit step function. That's why the unit step function is very important as a switching. We call it switching function because you can use it to mathematically represent signals that start at a certain instant of time. So if you want to represent this function, you have to multiply the cosine by unit step. If you don't multiply, then the cosine means that it goes from minus infinity to infinity. Okay? Some properties for the unit step function, if you shift it, for example, if you say u of t minus t naught, then it will be shifted right, and it will start from t naught, like this. If you shift it left, if you say u of t plus t naught, then it will be shifted left. It will start from here, right? If you reverse the t, if you take u of minus t, what happens? This is time reversal, right? So u of minus t, it will look like this. What about u of t naught minus t? U of t naught minus t. How does it look like? Think about it. U of t naught minus t, unit step of t naught minus. This is reversed. Now we replace t with minus t, so it's time reversed, and then we replace t with t minus t naught, so it's shift right. So it should look like this, right? And the last one for now, for the time shift, if you want to represent u of t minus t naught minus t, this is time reversed and also shifted left by t naught, so it will start from here and goes like this, right? You can exercise on these functions. I'm doing them quickly here in the lecture, but please make sure that what I'm doing is correct. Do it yourself. Make sure that what I did here is correct. Right. Another property is related to scaling. If I want to represent u of at minus t naught, how can I represent this? So I multiply t here by a. This is similar to u of t minus t naught, but I replaced t with at, right? I did the scaling. So you can start from u of t minus t naught, this one, and then when you replace t, when you replace t with at, what will happen is there will be a time scaling, right? So the function will either shrink or expand. How do we do that? By dividing the important points over the factor a. So if you divide the important points over the factor a, this will be t naught over a. So the function will start at point t naught over a. Wallahi, if a is larger than 1, then t naught over a is going to shift. It will be smaller than t naught, right? If a is less than 1, then t naught over a will be greater than t naught. So this is equivalent to what? This is equivalent. This is equivalent exactly to unit step of t minus t naught over a. It's like a unit step shifted by t naught over a. So u of at minus t naught, which is this function, is similar to unit step shifted to t naught over a. U of t minus t naught over a. So these are the important properties of the unit step function. طبعا, of course, this rule, the last rule, is for either a positive or negative, not for a equals 0. Okay, one thing here that maybe some of you noticed is that I defined the unit step function for t greater than 0 and t less than 0. I didn't talk about when t equals 0. What happens when t equals 0? And this is a very interesting question that has no answer. So people, they didn't define exactly the unit step at t equals 0. And it is not important for the work of engineering what's the value of the unit step function at t equals 0. Some authors, they defined it to be 0. They said, well, at t equals 0, the unit step will be 0. Some other authors defined it to be 1. And some other authors, which is I am one of them, or I believe in their opinion, they define that the unit step function equals half at t equals 0. And I have a reason for that that will appear later, maybe in the next video, is that at t equals 0, it's half. But again, this point is not important to us, and there is no single definition for this point. Okay? To continue with the unit step, let's talk about the integration of the unit step. If we integrate the unit step, what does it give us? Because this is very important. It will give us another important function. If we integrate the unit step, it will give us another important function that we will use later. So if we integrate the unit step, let's say as f of t, a function f of t equals the integration from minus infinity to t, our unit step function shifted, for example. Okay, or let's start with the unit step function just without shift. And if you want to integrate the unit step function and you have t in the limits of integration, you have to put here a dummy variable, right? So you can use tau, u of tau, d tau. So if you integrate the unit step function from minus infinity up to t, what will happen? It will be the same as integration from 0 to t, u of tau, d tau, and u of tau from 0 up to a certain instant of time t. طبعا u of tau يا شباب is you can plot it, you can imagine it how with a variable tau. It looks like this. It's 1 here. So if you integrate it up to t, it's a constant, right? Between 0 and t, it's a constant 1, d tau. So it will give you t for t greater than 0. If t is less than 0, the integration will be 0, right? Because if you integrate from minus infinity up to here, the integration is 0. If you integrate from minus infinity up to t greater than 0 for t greater than 0, it will be t. So the integration f of t of the unit step, it will be t only for t greater than 0. And it will be 0 for t less than 0. How can we write this? We can write this as f of t It is t u of t, صح? It's a function that starts from 0. Similar to the switching here. A function starts from 0, you can multiply it. You can represent it by multiplying it times a unit step. So the integration of the unit step will give you t multiplied by a unit step, which looks like this. It will give you a ramp function. This is what we call ramp function with slope 1. So before, for t less than 0, it's 0. For t greater than 0, it will give you t. Okay? So this is the integration of the unit step. What if we integrate a unit step that is shifted? If we integrate a unit step that is shifted, let's do it quickly. So let's say f of t, or let's say x of t, just to change the notation, it's the integration from minus infinity up to t, unit step shifted. Of course, because we have t in the limits of integration, we have to use another dummy variable here. So we'll use tau minus t naught d tau. First, let's plot this unit step with tau, the variable is tau, and it is shifted up to t naught. When you integrate from minus infinity up to a certain instant of time t, well, if t is less than t naught, the integration will be 0, right? If you integrate from minus infinity up to t here, less than t naught, the integration is 0. But if you integrate for t greater than t naught, the integration will give you this area. Right? So for the integration up to t greater than t naught, x of t will be 1 multiplied by t minus t naught. So it will be t minus t naught. So our integration x of t is t minus t naught for t only greater than t naught. Yani our x of t appears like this. Only for t greater than t naught, it will give you a line. How can we plot this? This is a line, right? A line with the slope 1. Line with the slope 1 that starts from t naught. And for t less than t naught, it's 0. This is how x of t looks like. How can we write this mathematically? It's a function that starts at t naught, right? So we can write this mathematically as x of t equals t minus t naught multiplied by a unit step that starts from t naught. So any function that starts from a certain instant of time, you can represent it mathematically as a multiplication of this function with the unit step. Okay, sure? And this is the integration. This is what we call a ramp function, ramp of t minus t naught. So this is ramp function shifted up to t naught. Okay? So the integration of a unit step is a ramp function. The integration of a unit step shifted is a ramp function shifted. We'll stop here in this video. Next video we'll discuss the rectangular function.